Hey everybody, short video here about scalars and vectors. You've probably talked about these in math class before, maybe not recently, but probably pretty recently. So we've talked about a couple of definitions: displacement, we've talked about distance, and we've talked about velocity and speed. And we're going to talk about how each of these kind of relates to the idea of scalars and vectors. All right, so that being said, we're going to talk about scalar quantities. So scalar quantities are numbers, essentially, or any quantity that is only described by that number. So it is just a number. So these things offer us some information about the amount of whatever that quantity is. A vector gives us more information because it doesn't just give us the amount, it gives us what direction as well. All right, so that could be positive direction, negative direction, up, down, left, right, north, south, east, west, or that way, or whatever it might be. It could be very specific or just general, but it gives us more information. The size or length of a vector is called the magnitude. So essentially a scalar quantity is just the magnitude of a vector quantity without that directional component. And we graphically represent vectors as arrows, which you may or may not know. Okay. Displacement vectors. So displacement vectors can give you an idea of how far you are away from your starting point. So we talked about the idea of displacement being your distance from where you started, and we can represent that by a vector. So if we look at this, this setup here, we get 12th and Vine downtown. So if we look at Jane's path and we kind of trace Jane's path out, we have the displacement vector right here, D3. But how did Jane get there? She probably didn't walk that blue line, right? This arrow, this vector, because that probably would have been walking through buildings, and you probably can't do that. So what we do here, we take a look at what made up Jane's path. So Jane's path probably, well, did start here. This is not cooperating. There we go. And went down 12th Street to the east, and then went up Vine, all right, and ended up at that final point. And so the total distance that Jane covered would be the two red lines, but the total displacement would be the blue vector, all right? So these two vectors, the two red lines, now I didn't draw arrows on both of them, I drew it just on the one, but we could say that this displacement vector right here is made up of these two component vectors. All right, these two displacement vectors added together equals this blue displacement vector D3. And then we have Sam, which is a little more simple scenario because Sam's just walking east. So if Sam starts over here, Sam starts over here on 12th and ends up further down 12th, going east. All right. So it's drawn from the object's initial position to the object's final position. Let me move that down so you can read. There we go. Okay. All right. Vector addition. So we kind of just did that with Jane's path, but if we look at vectors A and B, if we add them together, you add them head to tail. That's the most important part. You never have vectors tail to tail or head to head. It's not how they are added together. Vector addition is commutative. If you remember that from math class, probably long ago. So basically what that means is that A plus B, I'm going to put the vector notation up top here, is the same as vector B plus A. And of course that's true in regular addition, and it is also true in vector addition. So it says add B to A. So 1, 2, and 3 there show you how to do that, but if we want to do A, adding A to B, we would have to move some things around a little bit. You could do it the other way. So I'll do this down here on the left. Where am I? There we go. Okay, so if we do B heads down this way, where did that line come from? I don't even know. So that is vector B, and then we want to add vector A to this. So we come down, add it head to tail. There we go. And vector A kind of goes up this way. Ugh, that darn line again. There's vector A. And then our resulting vector, if you notice, I am doing something funky with that, making these straight lines, is that dotted line, and that would be B plus A. And if you notice, B plus A is the same as A plus B. It's the same direction, it's the same length. The overall picture just looks a little bit different. That's about the only thing. All right, so the same thing. You can pause the video, add these together, and see what the addition is, right? P and Q, P plus Q, you add them together. Which one are you getting? Well, of course, it's A. All right. Here's an example. Anna walks 90 meters due east and then 50 due north. What is her displacement from her starting point? All right, start with the sketch. That's always easy. The nice part about this is you can use a coordinate system, a coordinate plane, right? XY coordinate plane makes your life a lot easier. And then you have different points you can look at and help, right? So this is pretty straightforward. You're just doing Pythagorean theorem, right? That's really not that bad. But then you might be asked, because remember, if you're asking for the displacement vector, the overall displacement vector, well, a vector doesn't just have a magnitude. So you're not just looking for the length of this arrow right here. You're looking for the direction as well, which means the angle. So we want to go through and solve. Well, this will get you for the, bring that down a little so you can see, for the distance, right? And then you have to go through and use your trig functions, inverse tangent, which you don't need to use because you have all three sides. You could use inverse cosine or inverse sine and plug that in your calculator, making sure it's in degrees and getting the angle. So a displacement vector, a full displacement vector, looks like this: 100 meters at 29 degrees north of east. So you need to be very specific when you solve for this, because we could be looking at north of west or west of north, or there's lots of different ways to describe a direction. The angle alone doesn't tell the whole story. Okay, so be specific about that. All right, so that's all we got for vectors and scalars. We'll be talking about this quite a bit more as we get into some more of the physics. Thanks for watching.